big hypothetical question, but a very interesting one. What would you do to the aero of an F1 car if there were no rules? And I suppose where we start here, Willem, is really understanding what the current regs are like and how that restricts the engineers and designers. So can you outline what that looks like?
Okay. So the current regulations have, for example, minimum weight. Now, the engineers do struggle a little bit to get the cars down to minimum weight. They have to be relatively creative. But a lot of that weight is not just safety structures, but also the powertrain, which is quite heavy. It's the most fuel efficient formula out there by far, like much more fuel efficient than any road car, petrol or diesel based. So it's a very efficient powertrain, but it is quite heavy because of having an IC engine plus the battery pack, the electric motors and so on. And then the safety structures you have to put around those things, the protection from if the turbo explodes, all this sort of stuff you have to have. So if you could get the mass down, then the downforce to mass ratio would improve. And that's going to mean especially high-speed cornering will improve because you have a certain mass to accelerate around the corner. So let's say you take your 800-kilo car and you make it 500 kilos and you have the same amount of downforce, then the grip the tyres have has to accelerate a lower mass and you can get that mass around corners much more quickly. So that's one aspect. Then the aerodynamic rules are also quite restrictive. You no longer have simple shapes where you can and you can't have bodywork. You have CAD files you have to follow where you're allowed bodywork in a certain zone. You can have so many elements, this sort of thing. If they took those dimensional restrictions away, you would be able to add quite a significant amount of normal, let's call it organic downforce to give you more aerodynamic power. You would be even more efficient than we are today. And the reasons that the rule makers do that is so that they have a combination of a car that looks good, not something with loads of ridiculous appendages all over the place, and also a car that creates a wake that is at least possible to follow, rather than a wake behind the car that is so low, wide, and long that you just can't get close to a car in front of you. So the rules are designed to allow good racing. If you open things up, we're not even talking about active aerodynamics, but if you open things up a bit more, you would have a car that was much, much lighter and have a lot more downforce and probably a little bit less drag, probably, because you would end up with a bit less power, I would imagine. So then cornering speeds would be ridiculous, like hard to sustain. We're already getting close to 5G cornering again. And so once you go beyond a certain G-force, then it's quite difficult for a driver to stay alert. Yeah.
Sure. Okay. And you say we're getting back to 5G again. What have been the peaks in kind of aero performance throughout the years?
We were getting to a peak in 1994 when we were starting to get some really big accidents. Then Ratzenberger and Senna were killed, unfortunately. And at that stage, we were getting to 5G.
Really, in 94? And they were pretty simple cars when you take a look at them, but flat floors, right?
Flat floor with diffuser, really, as you point out, really quite simple cars. But we're getting to...
And quite light.
And very light, under 500 kilo-ish. So you can imagine with less aero research tools that we had in those days. We just didn't have the budget. We didn't have the knowledge either. But we were achieving quite high downforce nonetheless. So that was a peak, and then the rules were changed mid-94, and the rules have been changed a number of times, each time to try and slow the cars back down again. Then in 2017, there was a little bit of an opening up of the rules that brought the forces back again. And with these new rules, as expected, the teams have made quite rapid progress in understanding the regulations, and the cars have got a little bit quicker, and you're getting back again to the 5G cornering speeds.
And was there any point in between 94 and kind of 2017 onwards where it got close? Like I remember the cars of like 2004, maybe 2008. Were they kind of peaks in performance?
Exactly that. 2008, the cars are getting heavier at this stage, but 2008 were very, very quick. Then 2009 was designed to slow them down, but didn't so very well. Then you had another big change, 2014, where the cornering speeds were down a bit, but took a big step forward in horsepower. So the cars were quick nonetheless. But I'd say they were the pretty much the peak was 94. And then now.
Of course. And so you said that, like, you know, getting onto 5G, you know, are these peaks. But if we were to open up the rules, we would start getting really close on the driver having issues to drive the car. Is that what you mean?
So you can combat the G-force in an aircraft, let's say a fighter plane or a Red Bull plane. You can combat the vertical G-force you get. So when a plane corners, it will corner by rotating the plane and pilot. And so the G-force is always pushing the blood away from your head. You combat that with a G-suit that pushes the blood back up into the upper parts of your body. So your brain gets blood. Otherwise, you black out. But it's quite difficult to fight the sideways G you get. So braking is a very abrupt thing. It's very high G, but it's quite short in a Formula One car. It's a really short, abrupt brake, and then you go into a corner. But a long corner, and it's first always seen in oval racing and Indy, where if you have too much sideways G-force, the blood goes to one side of the brain, and there's no suit. There's nothing you can do to combat that. And then you start to lose vision on one eye that's connected to the side of the brain that doesn't have the blood. It's opposite. And eventually, if you keep going and you put your driver into an aircraft spinning simulator, then eventually a driver will black out. And that's definitely not what you want when you're controlling a high-speed missile.
No, I remember, I think it was in the 90s I can't remember the oval, but there was a circuit in the US for IndyCar or kart, I can't quite remember, where there was a weekend where, I don't know, 3 or 4 of the drivers were blacking out. It was a tight oval, but it was also very quick. So the sustained G there, they kept on blacking out and crashing. And I think they actually cancelled the event in the end.
Yeah, so that's something to consider. If you're making this amazing car, then you need to design a circuit with short, sharp turns in different directions, not always no ovals, because the driver will have control, and it takes time for the blood to flow across from one side to the other.
For the sake of this podcast and to not just finish it now, let's say that some technology is designed to keep the blood in our heads as we're driving around. And the real restrictions are kind of the box that a normal, you know, modern Formula One car kind of fits within. You can have as many twiddly bits coming off as you want. Where do you start, and what does that begin to look like?
So some parts of it will look like, so Red Bull have released a number of design studies, let's say, and the Valkyrie, the Aston Martin Valkyrie, is, let's say, an offshoot or a realization of some of those concepts. So the car would start to look a little bit like that. If you would allow then active aerodynamics, now those cars have active aerodynamics or are extreme hypercars are likely to have active aerodynamics simply to limit the downforce once you get to the point where the tyres can no longer handle the loads. So that'll be the next thing. In order to keep a tyre that doesn't weigh a ton like an aircraft tyre, you have to design within the limits of the tyre. And the hypercars that are on the books are all looking at releasing some of that downforce. So maybe opening a hole in the diffuser or winding off wings, things like this.
Sure, okay. And then, of course, you can ramp it up in the corners and give yourself as much downforce as possible. But to kind of take a step back, what, you know, if the rule book was open, what would the cars look like? I mean, would you? I suppose you'd close the cockpit. Would they, if the drivetrain was the same and in the same place, and the wheels and tires were in the same place? What would it even like begin to look like? Would it even resemble a Formula One car?
Not that much. So you would close the cockpit. It's a way to keep a stronger structure. You'd have to have some sort of canopy you could blow off, that sort of thing for safety reasons. But you would close the cockpit, gives you better control over the aerodynamics and a stronger structure when it's all locked in place, which you will need as well. And you would have a very sleek looking car, but fairings in front of the wheels, fairings behind the wheels. The wheels would not be truly exposed. You really wouldn't want them to be truly exposed. And the rear wing would still be pretty massive. Front wing, massive, not in the middle, but more towards the outside, so you can get some air rolling in underneath or around the front wing to go underneath the car.
Okay, so you would still have wings.
You would, yeah. The main plane of the front wing can be a very efficient device, 40 to 1, 50 to 1, something like that. It can be very, very efficient, the main plane.
What do you mean 40 to 1, 50 to 1? What's that ratio?
The aerodynamic ratio of the downforce that it generates compared to the drag that it induces or creates.
Sure. Okay. Yeah. So you can be super efficient with that. And would the wing have 15 elements, or would it be one element that's huge? Where would you go with that? 4
or 5 downforce generating elements on the front wing and some flow control vanes, a little bit of the concept that we had up to 2018. They were banned for 2019.
Are these the front wings that were super detailed and kind of ramped up quite quickly and had many elements actually? Yeah. What's the reason for having so many elements like that rather than one kind of smooth element?
One element would simply stall and let go, be very inefficient. At a certain point, it would let go. Every extra element introduces a fresh boundary layer, we call it, a fresh layer of clean air that can be turned a little bit more each time. So starting again, and then... So one limit is you can only turn the air so much with a single element.
Because the air would fall off the back of it.
The other reason is that you need a fair bit of power, so you want to turn the air a lot. But also the front wing main plane will be in ground effect, so it'll be quite sensitive to changes in height. And each element behind it is far enough away from the ground that each element is even less and less influenced by proximity to the ground. So the car will generate multiple tons. Already we generate over a couple of tons of downforce on a Formula One car. So you'll generate lots of force. That force will not only just push the whole car down on its suspension, but also reshape the elements. And those forces shouldn't be super sensitive to ground effect. Eventually, if any element that is close to the ground, eventually if you push it too hard, just like we had with porpoising on the 22 Formula One cars, eventually you push too hard, you get an element too close to the ground, you just don't let enough air through between it and the ground, and then it will let go. So to make the cars less sensitive to ride height, so typically speaking, a Formula car, let's say, will be more sensitive to front ride height than it will be to rear ride height, because you've got a rear wing that is far away from ground effect, whereas the front wing is nearly always in ground effect. It's the most efficient place to put it. So you don't want, at high speed, the balance to be moving to the front.
Okay, understood. Because it's closer to the floor, it's more affected by it. Okay. And when you're talking about the front wing like that, I'm thinking, so the air comes along, it hits the front wing, and you're trying to basically keep it stuck to each element as it kind of goes through. During that, is the air slowing down? The first part of my question. And then the second part, can you use it up too much and then not be able to use it further down the car?
Number one, on the upper surface, we're talking motorsport. So on the upper surface, motorsport orientation, the air is being slowed down. You're putting a brake in front of the air, you're slowing it down. On the underside, you're squeezing the air between the main plane, the front wing forward element, main plane, and the ground. You're squeezing it, and by squeezing it, you are accelerating the air underneath the main plane. So you're slowing it down above and you're speeding it up below. But is there a danger of you using too much? Yes, and that's why you would tend to have the downforce generation outboard. And so by having the downforce generation outboard, you then have less upwash inboard. That creates a flow rotation, a vortex or two vortices, and that flow rotation takes air that would normally pass above somewhere near the middle of the front wing, that is being rotated inward and downward and goes underneath the car.
So that's why you don't see more elements in the middle of the wing, because you want it to continue its path down under the car.
Now, with the current generation of Formula One cars, they limit how much you can do. Let's leave it at that.
Okay, that sounds interesting, but I'll leave it. I'll respect that. I'll leave it there.
They don't allow you to go as far as you would want to go. You have CAD surfaces. You have to have elements in a certain area of a range where you must have and may have elements, and a range where you may not have elements. So
back to our hypothetical car. We've got the wing. We'd probably go, what did you say, 5 or 6 elements. We'd have wheel covers on there. Is that to stop drag and control where the air goes after the wheels?
It's the drag. Yes, the drag's important, but it's really about flow control. Yep. So wheel covers, and you might have a non-rotating wheel cover on the front to exit brake cooling air in a particular place. So it's a wheel cover, but it does not rotate with the wheel, and it exits air in a specific place.
Because it comes through the hub and pops back out the other side, and then you want to direct it somewhere.
And you would have to cool the brakes, of course, as well. So you use that to cool the brakes. You use the air as well to manage the rim temperature, to help manage tyre temperature, and also control where the exit air goes.
But speaking like a true aerodynamicist, cooling the brakes is secondary, right?
Well, it is until you're driving the car and you've got none. Then it's primary. And so cooling, that's primary safety. Avoid the accident.
So in terms of the nose, would we go back to something, I can't remember how long ago, would we go back to like a high nose? Actually, I think you were, was Benetton were the first ones to do that in 94, right? Go with the higher nose to create some more space.
Tyrrell created a high-ish nose with the wing coming high up off the nose. We were the first to have a high nose separated from the wing, so you have a relatively clean nose shape, and use the shape of the nose to let air wash underneath, accelerate underneath the nose and generate some downforce from the underside of the nose, even though it looks like that's not what it's doing, it was. And so you would probably not go as high. I think we've learnt a lot about safety since those days. When we originally, was me just putting a limit on the nose height. I looked at the minimum height of a cockpit, no matter what, and took the height of the nose, and I said, right, the maximum height I'm prepared to go with the tip of the nose is 50 millimeter below that very lowest ever theoretical cockpit height.
So back then there were no rules over the height of the nose.
But I just decided internally at Benetton that's going to be our limit.
So there had been no kind of develop. So my question then is, why did the noses come down?
Safety. So the noses came down 2016. I can't remember exactly what year, but around then, and they were really ugly. We had a few goes at it, but they were really, really ugly until everyone got their heads around what they needed to do. But the reason is this. If you take a relatively high nose, so the nose that I would have designed on the 92 Benetton, which was the first really high nose Benetton, if that nose were to crash into the back of a rear wheel, so you're driving along and you get into the back of a rear wheel of another car, then it's going to be a little bit below wheel center height, but somewhere close to wheel center height. That tyre, because it is rotating, is going to be rotating tail upwards. The rear of the tyre is going upwards. That nose is going to be sent skywards. And so we'd had one or two accidents like that, and the theory said that's what would happen. But we'd had one or two accidents, and that's exactly what happens. And it's a scary accident in every sense. Whenever a car goes flying, you have lost control of the accident. There's too many parameters to predict where it's going to go. And to get the nose to go under the car behind, so let's say your nose hits a tire and you've got a really low nose, you will pick the rear tire up. But what's that going to do? Your car is going to be braking hard, and you're suddenly going to have extra braking, because of front braking anyway, because of the power of the car being pushed down. The rear car will be pushed tail up, but aerodynamically, that's going to give it more drag and more incidence on the aerodynamic surfaces, and it's going to keep it on the ground as well. So both cars stay on the ground. And that's why. So the FIA did some really intelligent research into nose heights crashing into a rotating wheel, and they worked out the height we need for preventing cars flying from that type of accident is a certain height, and that's why we have the low noses. And I would probably stay with that. But there are tricks you can use for safety reasons, but there are tricks you can use to get aerodynamic advantages.
There were some scary crashes in like the mid 2010s, I think. I remember one with, I think it was Schumacher at Montreal, where they were nose to nose, and it kind of skimmed up one car.
Yeah, that was really scary. But Mark Webber went flying. That was at different braking distances. He didn't expect the car in front to brake. They were having tyre issues and were hitting the brakes early. Both drivers were shocked that they had an accident, but it was slow enough at the time that it didn't do massive damage. Both drivers walked away. No one else was really involved, but the potential was there. And one of the things I do adore about motorsport and the way the FIA approach it is that they do look seriously at anything that is safety related.
To just go quickly back to 1992. So back then, there were no regs on the height of the nose, and no one had thought to, apart from you, I suppose, put the nose a bit higher. Why was that? Was it because they needed the structural strength of the nose to come down and support the front wing?
I think all the structural engineers will have understood there are ways, but they just hadn't made the connection, really, I think, between the gains you could potentially make by just separating the wing from the nose, and the fact that you could then get a lot of clean air going through to your floor. They hadn't really thought about it. And it was only in 95 that they introduced the step floors. So up until 94, the floors were in any case quite low. And so you could only get a certain amount of air underneath. But we noticed we weren't getting too much air underneath the floor. We felt so it was for us relatively early years. In 92, we'd only been doing CFD for a few years, but we were noticing we're not getting full energy of air underneath the nose of the car. And I think it's maybe the introduction of CFD and the fact that makes you think about what could we do to improve things. That was one of the key things that made me think about it.
Did that open up? Like what was the difference when CFD started to come in terms of like the output or the number of tests that you could do? Was it a 10x difference, or was it just a small increments?
First, it was incredibly painful to do, really slow to do. Nicholas Tombazis, who now works for the FIA in charge of single-seater matters, was my first full-time CFD engineer at Benetton. And it was painful for him, 3 weeks or so, for him to create his first running CFD model. And so we weren't doing a lot of tests, but what it gained immediately, CFD gives you a lot of ways of looking at the airflow in detail that's just too difficult to do in the wind tunnel, or was at least at the time. And even today, if you want to look in detail at the airflow underneath the car, it's quite difficult with a laser to get under there to have a look and so on. And so CFD gave us an incredibly detailed picture of the airflow around the car and what pressure it is, what energy it's got, what direction it's going. All this sort of stuff was just like, oh, I want more of this.
I'd never even considered that, to be honest. What you say about just physically seeing the underside of the car, because you see a car in a wind tunnel, you see the smoke going over the wings, and it all looks great. You never really think that in parts you struggle to get under and actually have a look at what's going on with the car, and CFD opened that up. That's fascinating. So let's head to the kind of middle of the car, the overbody now, with our hypothetical question. I suppose we're going to have radiators, I think, unless you could put them somewhere else. But let's say we've got pods. Would we, big pods, small pods, and more interestingly, would we go back to something that looked a bit more like 2008 with lots of little small pieces and details coming off the car? Or would it be something nice and smooth?
So we've learnt a lot. For example, 22, 23. I've seen side pod entries in every location you can imagine. John Barnard invented or decided he wanted separated side pod entries on the Ferrari in 96, which was really, really interesting. So they're two oval entries that are separated from the chassis, so you don't have the slow-moving air that builds up along the sides of the chassis going into your entries. But we've had all sorts of things. And for example, we learnt in the 90s that if you have a bit of a bluff leading edge on the lower part of your radiator or side pod start, then that rams a little bit more air underneath the car. And
is that like a little gate at the bottom of the entry to the pod?
Not so much a gate, just a surface, just a blank surface. And then from IndyCar, they were the first. IndyCar started to put these funny fingers in front of side pods in front of the floor. I thought, what the hell? And they're vortex generators. It just rolls up a vortex. And rolling up a vortex is actually not very efficient, but in itself compared to, say, an aircraft wing. But rolling up a vortex means you get some higher velocity air. And where you've sped the air up locally, the pressures on that high speed section are a little bit lower, the static pressures, the surface pressures, if it's in contact with the surface. And they're a little bit lower. And so you can use that to get a little bit more downforce out of the air. And so we've learned all sorts of little tricks. And so you ended up with, so for example, 2018, if you look at the leading edges of the floors of the 2018 cars, they had a nice sort of radius leading air underneath the floor, but they also had, using some trickery in the regulations, some vortex generators on that leading edge using the radius rule to just have 4 or 5 little vortices that would roll up going down the floor. And so the side pods on our car then would probably be quite high up, as close to the chassis as possible, relatively small entries. You don't want to go so wide that you're picking up dirty air that's been anywhere near the front wheels or the front brakes, because it's going to be warmed up and it's going to be turbulent. So you want relatively high energy air. And then a trick that we learned that we all have seen work in 2023 in particular, but 22 and 23, Mercedes tried some unusual side pods. They made an improvement from their baseline, but what has been the dominant influence is you take air, you bend it down towards, so if the air's coming towards me, you bend it down as it goes towards the rear wing, and then you get to the lower rear wing and you kick it up really aggressively. That lower rear wing is a terribly inefficient device if you consider it alone, but it creates a reduction in pressure behind it that turns on the floor. And so you would...
Right, that's why we see these big ramps up on the beam wing.
And so you would have a multi-element, so you're restricted in Formula One to a couple of elements. You would have a multi-element, a little bit more efficient. Then the other thing that you don't have enough freedom of in Formula One that I would want is you would want the trailing edge of your floor to stop just at the peak of low pressure area on the underside of your lower rear wing, and the upper rear wing would be positioned so that it also enhances the reduction of pressure underneath your lower rear wing. So you might have your upper rear wing forward of your lower rear wing to get a nice airflow between the two, but your lower rear wing would be further back so that it could really draw on the floor. And the thing is, we're talking about the leading edge of the side pods, but actually it's all related. It's all interconnected, of course.
Sure. So we're not talking like massively different from what we're kind of seeing today. Like,
no, sleeker looking, and you would take advantage of being able to cover the wheels front and rear. And then your bodywork, all your bodywork would be as wide as the wheels, as wide as the car. Maybe even a bit wider.
So the pods would be out towards the outer edge of the...
You would have structures.
Okay, structures on like just sticking out, or... Oh dear, okay.
Yeah, exactly.
Yeah, like the X-Wing. Like
the X-Wing,
stuff in the late
the
90s.
X-Wing was magic. The X-Wing was really interesting because the X-Wing, so if you look at the rear wing assembly, you sometimes see the tip vortices when you have moist air. You'll see the strongest vortex visible as the moisture in the air condensing into mini droplets, which then become visible. So just high moisture content, high humidity you don't see. But once you get to small droplets, you can see. And so the humidity gets pulled out into droplets in the vortex, and you can see that. And the X-Wing had a vortex, just like our rear wing would have a vortex each side. But the inboard vortex rotated air, so you got more air to your main rear wing. So they had that benefit of generating downforce in the middle of the car was completely insensitive to ride height because it was so far away from the ground, like zero effect, effectively, zero influence from ground proximity, and it gave the upper rear wing more power. So they were magic.
Right, so it's a double win, basically.
Okay, the loss is drag, but it gave you a lot of power that allowed you to get more power out of the floor and made the car more aerodynamically efficient.
I can't remember, how long did they last for before they were banned?
Less than a season, 2 or 3 races. And then Charlie Whiting at the time envisaged, now what if certain failure modes happen and this wing bends down onto the driver, or you have an accident and it gets shunted into the driver?
And that makes sense, right?
We had to say yes.
So onto the floor, I suppose, one of the main drivers of downforce. Are we saying we'd go with fans or not with fans?
Honestly, if there are no limits, fans.
Okay, let's do both. Let's do with fans and then what you do without fans, because I always feel like fans is a bit, it's cheating.
Oh, it's cheating big time. It's not a little bit. It's a big cheat. But yeah. So we've learned. So you could, for example, go back to using the exhaust. So we were using 2010 and 11 in Formula One, where you put the exhaust beside the rear wheels, just beside an inboard of the rear wheels to energize the floor. Suspension would have to be adapted to stop that creating throttle position sensitivity on the balance of the car. But you would introduce that. And if you were using passive aerodynamics, then the floors would look conceptually like the floors we race today, but quite different because they are you are very limited in where you can and where you can't put bodywork with the floors that have been designed by the rules of today. But the concept would be a ground effect floor with a lot more design freedom than the Formula One regulations allow today. And that would give you more power than you have today with a little bit better control.
So aside from it being, a big wing underneath the car, what else, what would it look like? How would that differ?
You would still have the strakes you have today that create, so there are an outer wall and 3 strakes that all the Formula One teams use to create a single, massive, very powerful vortex that tracks down the floor and goes all the way and out the back of the floor. And that vortex creates that speed up that gives you a significant reduction in pressure on in the air that is close to the surface, or the upper surface of the diffuser, the floor, and that pulls it doesn't push the floor up the way normal atmospheric pressure would be pushing against the floor, and because of that, you're being pulled down. So it's not actually negative pressure that doesn't exist. You have the vacuum, you can't go beyond the vacuum, but you are not resisting aerodynamic pressure, standard air pressure from underneath anymore, and therefore underneath is being pulled down. You have a partial vacuum on the floor.
Understood. Is there anything in motorsport that is similar to what you would do without any regs? Like, is the hill climb cars somewhere close?
Hill climb cars are closer. So with hill climb cars, the disadvantage you have is nobody has the budget to spend millions on aero research like you do in F1. Nobody. And over time, people have spent a decent amount. But for example, the spend on the Empire Wraith that we're using as the basis for the project Inversion, that was very modest compared to what a Formula One team would spend in a month, for example. Very modest. It's a very small budget. But of course, you're using ideas from people with experience. But the rules in hill climbing would allow you to do much more. Yes.
With our floor for this car that doesn't have any rules, would we have any skirts down the side of it? Would they be necessary, or could you do that with the airflow from?
No, you would get a benefit by having skirts at least over part of the floor. So if you use the Formula One floor concept, there is a part of the floor where you actually want air to flow out from underneath the floor, because you actually send a lot of air in. Some of the energy in that air is being used to generate these vortices, and some of the low energy air is then pushed outboard. So you don't want skirts on the part where the air is being pushed out. And then you would get a benefit, an aerodynamic benefit, from having something to bridge the gap to the ground, something. A movable skirt or a sliding skirt or a flexible device, that would give you a significant benefit to then create a proper seal. You never get a proper seal. If I do an experiment on it in CFD for, say, the hill climb regulations in Australia, where you don't have a ground bridging restriction, you have no minimum ride height, then I have a gap of 3 millimeters and I allow air to go through that gap if I test in CFD, because you never have a perfect seal. So let's say 1.5 meters in front of the rear wheels, you would want some ground bridging device of some sort, and the benefit is significant.
Really? In like 10% or more?
30%.
Wow. From just sealing the... Wow, that's incredible.
Pity you can't do it, eh? But we can in our car. We can for our car.
Yes, we can. We can and we will. And in terms of what the floor would actually look like, right? If you look at the back of a modern F1 car, you see kind of the diffuser coming up like this. Would the optimal shape and size be something like that, or would you push it even further?
Okay, that's a difficult question to answer. I love the question. That's really good. So it depends on the freedom we have with the suspension of our car. If we have an intelligent active ride height system like we had, say, in 1993, was then banned, or even, let's say, a platform control, rough ride height only, where you roll is managed by let's say, more conventional means, but you at least had height control, then actually the floor could look simpler at the back end than the current generation of Formula One floors. The current generation of Formula One floors have a number of different ramps and areas where what you're trying to do is to reduce the ride height sensitivity of the floor, because from 2022, for the first time, the rules have allowed us enough expansion that we can get to the point where the floor is sucking as hard as it ever will, and then it suddenly will get a reduction in downforce where one of the two vortices bursts. So those two big vortices we roll up, one of them will burst, and then you get a stall of the flow. If that happens, then the car bounces up on the suspension and gets drawn back down again once the aero takes over. And it can be quite, to a driver, it feels pretty damned uncomfortable. And from a grip perspective, it's also not what you want if it ever happens when you are grip limited. But if you have platform control, you use that to manage, and then you end up with a simpler shape. You just focus on getting the best aerodynamic shape, which is a simple, smooth shape. If you look at the floor of the Wraith, it's actually a very simple shape. It's just been designed with a lot of care to try and get the expansion control nice. And it also has a limit. It has an optimum where if you go beyond the optimum, it will also let go. So we have to make sure with Packers that we don't ever put the car actually on the ground.
Yeah. Okay. It's interesting what you say about the simple shape. So am I right in thinking that, if you'd stripped everything away from a race car and actually made it just a wing by itself, the most efficient shape is just like an aeroplane?
A little bit like an aeroplane wing, but so you want a vortex under there, and you only get a vortex under there if you have some structure that creates it. Whereas if you just take an aeroplane wing, put a plank either side of it right from the beginning and just have a conventional aeroplane wing, you don't have that additional rotation caused by a vortex, which you do want for getting the maximum efficiency.
So when you're talking about, starting the vortex there, is that when we see like a strake, like a strip of carbon on the underside of the front wing, for example, or do they start further back?
They can be for generating a vortex, but the vortices the vortex that is generated under each half of the side pods of the Formula One, the floors of the Formula One cars today, they're created by the strakes that are at the leading edge of the floor.
Okay, it's like these fingers that come forwards. Okay, so they're at the front of the floor. And then how many of those would typically be? Is it, you've got a certain amount of space on there and it's possible to create a vortex of a certain kind of diameter or size, and then you have to create multiple of them?
So a vortex is round. So if you have complete freedom, you make space for your vortex, whereas the current regulations in Formula One have effectively like a line where we have like a choke point that you're forced to take bodywork across a big width down to a certain height. You might not want that height to be the same at every Y station across the floor. You wouldn't. You would have a sort of a shape that allows the vortex to work over a bigger area of bodywork.
Sure. That's fascinating. Okay, so next question. We do have fans. Does the floor look the same, or is there another kind of structure, another shape that you would use if you didn't need to generate the aero, organically?
So this is where I get into a limit to my knowledge because I haven't done the experimentation. So one of the things I've learned in life is theory takes you a certain distance, but we're still evolving. Aerodynamicists around the world are still understanding and evolving the theory of aerodynamics. It's deliciously complicated, and there are certain things I have confidence in. When it comes to using fans, my level of confidence goes down because I have the theory, but not the practice. Now, the theory says we can go down to as close as you can achieve and to a vacuum over any surface. So in theory, we can go to creating 10 tons in theory. If you've got a high pressure atmospheric day, standard temperature and pressure, close to 10 tons for every square meter of surface area that we have in any area that is being driven by a fan. The truth is the fans are not that powerful that they can remove all the air. You effectively have to remove the air. It's as simple as that. Yeah. But of course, that isn't simple. Leakages become really important. So the McMurtry car that is an amazing, when you go and see it, it's a really small car, a really interesting concept. Somebody had to do it. I'm really pleased that they did. But for example, you have to be incredibly careful on rough surfaces. You wouldn't be able to use that on a rally, for example. It would just not be realistic. And you have to be very careful not to hit curbs or any sudden steps or anything like that. If you damage the effective seal they have around their fan, then you're going to do a lot of damage to your downforce. So you have to find some sort of compromise. And also, the most powerful fans in the world, the more power you use for your fan, the more power you're taking away from being able to drive the car forward. So you have to find a compromise. But the first stages, so getting to 20 or 30%, let's say 30% of a vacuum, I would say should be achievable. And if you imagine applying that over, let's say, 4 square meters of area, 3 tons per square meter times 4 square meters of area, that's a lot of power. That thing is going to go around corners like it will do whatever you tell it to do, whether you want it to or not. Yeah.
Sure. Yeah. Okay. So is there a what does a modern car produce roughly?
About 2 tons, and about let's say there are certain areas of a Formula One car that will produce 1.5 to 2 tons per square meter, certain parts, but other big areas that are producing much less. So let's say average pressure at high speed over the entire underside of the car, probably in the order of 0.5 ton per square meter.
Yeah. So then it becomes like, what happens if the driver could do it, and the tires could do it, then the power becomes the problem, I suppose. I mean, this is a stretch of my mind to even think about that, but it would be so fast.
So you can just imagine the
good.
steps. And we've been here before with these steps. If you produce a massive step forward in downforce, what's going to happen to your use of the power? So I'll give you the reverse example. We went from 1,000 horsepower turbocharged engine to a 600 horsepower normally aspirated Cosworth engine at Benetton in 89. And going from, or 88, but anyway, going from 1,000 horsepower to 600 horsepower, our average throttle position changed from 52% throttle to 72% throttle. So suddenly you need to have a bigger cooling system, because you think about your cooling system by thinking about, okay, what's the heat rejection of the engine to engine oil, engine, whatever systems you've got, or batteries, and you think about the heat rejection to each system, and then what's my average velocity, and at least on average you can allow the thermal capacity of different materials to average out your temperatures, but on average you've got to cool whatever heat you get put into the system. And you go from 50% average throttle position to 72% average throttle position, let's say, then you're going to need a much bigger set of radiators to cool everything. You're going to need more air as well to cool everything. So these are delicious interactive steps that you have to put in as you imagine the different. And if you haven't imagined all the steps, then you're going to fall over.
So if we give it double the downforce, what's the next problem?
It'll be tires. Now, and that's where, of course, and that's why tires evolve. You do your contract, or F1 will do their contract with the tyre supplier, and the tyre supplier is requested to do certain things. Like, for example, Pirelli were requested to make tyres that do degrade with use, that are difficult to manage. They wanted that. The rule makers wanted that. They didn't want a tyre that was just perfect the whole time and consistent the whole way through, because no one would change them. You put the best tyre on, you don't change it. And maybe you would force them to do a pit stop, and then they would just wait till the right moment in the race. They'd wait till the last lap for the safety car, for example. And if it didn't happen, okay, everyone stops on the last lap. Well, that's not good for racing. Yeah. So the rule makers wanted tyres to degrade. But if you literally take a tyre, you're already pushing tyre construction and manufacturing and technology to the limit. With the current Formula One cars, you then imagine doubling the downforce, and you ask the tyres to cope with much more load. Even just structurally, what stops them flying apart? What stops them being crushed? If you look at the way touring car racing works, for example, if you push a tyre too early where you don't have tyre blankets, you push a tyre too early when it's still cold and it's not up to pressure yet, then you risk damaging the structure, hitting a curb, things like this. And you'll have a puncture later in the race because you've fractured part of the structure. So that would be a risk, that you fracture parts of the structure of the tyre if you don't change something in the tyre. You would have to make a stronger tyre. And that has ramifications. A stronger tyre will tend to be a little bit heavier, more structure. Then a heavier tyre won't perform so well. And that's why you're always chasing this loop.
Yeah, of course. Yeah, put more load through the car and then it's going to be more difficult. I've actually... on some of the old F1 cars that I've tested, we've turned the tyre on the rim and then got a puncture after that because you've pushed too hard too soon and not got them up to pressure properly.
And you get a puncture because you're sliding, the thing's moving, and you create a little bit of temporary gap, air escapes, and yeah,
and then that's it. I actually was thinking for this series of videos, getting somebody from Pirelli or Michelin or somewhere to come on and actually understand what is the other side of the tyres. Because we obviously all hear that, yeah, of course, Pirelli are making these tyres. They're not actually quite as good as they possibly could be. But how much further could they actually go? And I think that would be a really fascinating conversation. Could the cars go at, flat out qualifying pace for an entire race and the tyres?
Well, I don't know that they could, but they're the right people to ask. And there are some really senior people in each team in Formula One who are tyre experts, who've spent maybe half a life working for a tyre company at a high level, and now work for the teams in order to work out how to get the best out of a tyre. And those people are in high positions because understanding how to get the best out of a tyre is one of the most important aspects of doing well in Formula One. Aero, of course, remains pretty much number one. Powertrain and aero remain number one. If you aren't in the ballpark on either, you're nowhere. But tyres are also way up there, really important.
Yeah, of course. So, the back to the fans and the floor. Would you still run, like a ground effect style of floor with the fans, or could it just be flat?
I would say you would if you relied entirely on the fans. Then you would have a system that was inefficient at relatively high speed. At high speed, you can take advantage of conventional aerodynamics where you've got the drag anyway. Now, that's why I said at the beginning when you start talking about fans that you've reached the limit of my knowledge, because the relationship between the power you can reliably accept, aerodynamic power you can reliably create with fans, and the power that they draw, I'm not quite sure of that relationship because I haven't done the research. So that would be one of the first things you do, understand how much do you want conventional aerodynamics and how much do you want just a powerful fan? Because with a powerful fan, you'd end up looking totally different. If you just said fan only, then you put your suction where you want. You have a little bit of maybe a front device or a rear device to change the aerodynamic balance of the car to suit the driving conditions. And you throw away all your wings and all the drag that they bring, and you use that power instead to drive your fans. But it's how you manage that.
And if you, this is a bit off the wall here, but imagine you had a number of fans on a flat surface on the underside of the car. If it started sliding, I don't know if it would react quickly enough, but you could maybe move the power of the fans around the position of it to get rid of the oversteer.
That's exactly the sort of thing you would do. That you would, and so one of the things we're learning from, say, my links into Formula Student, looking at the very best four-wheel drive, electric, and now autonomous cars, they're able to react. So human reaction time typically is 0.2 of a second. And we can't really, the best drivers in the world don't have better reactions than, even if you said 0.15 seconds, it doesn't matter. The best drivers in the world are never going to be better than about that. The rest of it is anticipating what's likely to happen and being ready for it. A good control system can work in, let's say, 1,000th of a second. And that's getting better and faster all the time as computers become smaller and lower cost. One of the things that's happening is the clock speed is increasing. And the clock speed is fast anyway. And so you sense that something's happening and you react, and you can pre-program what you need to do to get the grip back. And you would need to pre-program, for example, if you're getting understeer, then you would need to pre-program that you need to give the front a little bit more grip to make sure that the driver does not have to change, because his reaction is still going to be 0.2 of a second. So he doesn't have to do anything. You just fix it for him before he gets there. And you could do that for sure.
Yeah. I actually had the similar conversation yesterday with Eloy Rosset from AMZ Racing, the former student team that broke the 0 to 100 kilometers an hour record. And yeah, it was fantastic. It was absolutely fascinating speaking to him. And they actually ran 2 fans on that car, right? That's how they got the initial traction. He said they'd actually budgeted for 6 fans and they didn't need all of them in the end, which was interesting in itself. But we were talking about the 4 motors inside the hubs and being able to control each wheel independently as you went through a corner. And I just found that fascinating because those motors are steering the car before the driver really knows what's going on. And so for me, I actually, it's one of those things as a driver, and I think you'll understand this, William. You told me a story once about putting a manually controlled single or an extra rear brake on the inside wheel of a car to get it to turn around hairpins. But when it's electronically controlled, I imagine that the feeling would be very, very unusual. And I don't know whether I could remove that kind of initial reaction to correct a slide, or whether you'd even have time to think about it before it was corrected for you.
The torque steer that they put in, or the control that they put in, the correct strategy, I believe, is to first balance the car mechanically without having any input from the motors as such, and then once you've achieved the best you can, then the motors, the computer systems look at what the car is doing and try and make the car do what the driver is asking it to do. And so you don't have to make any corrections because the car's just doing what you want it to do.
So it does what you want it to do, but it just does it more than it would do if it was all just mechanical. What you're saying. Okay.
Every trick you can to get the balance you want, to get the car to follow the direction you're asking it to follow. And then
okay.
There is a point, you can imagine, if you're doing 100 mile an hour and you just say 90-degree turn, it won't do it. Yeah. And so there is a point where you have to have strategies in place to try to make sure that the thing remains safe as well while you're doing your maneuvering.
Yeah, of course. I still struggle to kind of comprehend how that would feel. I think I just need to try and experience it.
What you're going to have to do is get them to put you in their Formula Student car. I would one of those cars, one of the top Formula Student cars, and there are a number of teams. I don't know who's top at the moment, but Zurich are up there, Delft are up there, the Greens from Stuttgart are up there, the TU Munich are good. There are a lot of universities that are really good four-wheel drive electric cars. I think they'll be really fun to drive them and say, like, turn off the torque vectoring, let me drive it, feel it. Now go to the same, and especially if they have you have a track you can go to, and it wants to be somewhere tight and twisty. And so the Formula Student tracks, which is what it's designed to cope with, they'd be fun to try.
I'm going to actually go to one of the events this year. I'll probably go to Silverstone or something just to go and have a look, because I've not been to one yet. So I really want to go. And it's, speaking to you and Eloy yesterday, I just think, it's such a cool and interesting concept, and there's so much incredible engineering going on. So
probably Silverstone's a great one to go to because it's here. Yeah, there are a lot of cars. It's a lot of fun to go to. The biggest in the world probably would be Germany. That'd be one to go to. But if you're going to drive a car, you want to wait till after the Formula Student season is over, and then go into one of the very best cars and get a private driving session with them.
I'll reach out to a couple of them, see what we can do. Right, so back to the. I got a question again about the floor. Do you know how much? So I was thinking about the fans and how much volume of air they're kind of shifting or would have to shift. How much air is going into a traditional, like, modern Formula One floor, and then actually coming out the back? Oh, we're doing public maths, Willem. That's brave.
So if the car's doing, let's say, 100, let's work at 100 miles an hour. Yeah. And you have 100 mil by 400 mil. 40,000 square millimeters. I'm going to do it another way. I'll work in square meters. 0.1 times 0.4. So you got 4% of a square meter. But you're doing, let's say, why don't we say 60 meters a second? That's 180 kilometers an hour. You got 2.4 cubic meters of air going underneath one half of the floor of the car every second.
Sorry, can you say that again? I feel like I'm watching Carol Vorderman on Countdown.
2.4 cubic meters of air going underneath the car every second.
2.4. Okay.
That's a lot.
Okay. Yeah. Yeah, that is a lot of air. It's a lot of air for a fan.
If you think of
right?
a workshop compressor, we'll talk in cubic feet or cubic meters of air a minute, not a second, but a minute, typically speaking. Yeah, there's so many CFM, cubic feet per minute. 2.4 meters cubed per second is a lot of air.
And that makes sense then when you say that at some point, even if you had fans, you would move to organic aero because it would be more efficient.
I need to do some research. Yeah.
And would that research be on how much air a fan shifts, or how much it can?
The first thing you do is you do a little bit of a research into who's supplying fans, how powerful are they, how much do they weigh, and there's some really good remote control aircraft fans out there for driving electric aircraft or electric remote control aircraft. There's some fantastic fans, carbon fiber, lightweight, very powerful. There's some really nice fans out there. You start there and you see what they can achieve, and then you program that into CFD and you start to do some basic experiments.
Yeah, because of course you still have the same problem. Like even if you had at low speed the fans running in the floor, you've then got to move the air somewhere out and still try and make use of it, right? Okay, let's wrap things up and finish off with the kind of the rear wing of the car. Would it, if we did have that huge dimension at the rear where we kind of came up to the outside of the tires, would it run all the way across? Would it be organic? Would it be in the body, or would it be kind of like a separate rear wing like we see in that nowadays on modern cars?
It would be a separate rear wing on its mounts, on sensible mounts. You would use the full width, but it would not be the same. It would not be an extrusion. It would not be the same shape and angle everywhere across the car. So, for example, behind the wheels, the air is in any case flowing back over the wheels and back down. So your average airflow direction is sort of downwards. And so if you've got a rear wing there, you can afford to reduce its angle. And in fact, you would need to reduce the angle a little bit so you're not turning the air too much. But the fact that the air is flowing downwards means your rear wing out there can actually be much more efficient than it will be in the middle of the car.
Right. Okay. That makes sense. So you would then mirror that with how the wing would look and how it would be angled.
And having a wider wing, if you've got a certain amount of downforce you want to generate, if you take a wider wing to generate it rather than a narrow one with a high angle, you can go for a wider one with less angle, generate the same downforce, and the amount of drag you create is lower. So it's more efficient to go wider. And that's why, for example, gliders, glider aeroplanes have very wide, the most extreme ones have very wide, really quite small wings, but they're really, really wide.
Yes. Okay. That makes sense. So it always comes back to the same thing. Every time that I speak to you, it kind of always pops into my head that, it's not just about putting more and more downforce on the car. It's just ensuring the efficiency of that downforce so that you can go quicker than 60 miles an hour with all the drag. Yeah. And
to one little note about fans versus organic, the latest European Formula student cars where fans are being allowed, those kids studying that are working out what the compromises are. They're going down that road.
I actually hadn't realized that it was being allowed in Formula Student.
There's some competitions where it is being allowed.
Wow, that's fascinating. That's absolutely fascinating. Oh, I'd love to look at some of those cars. I'll do some research on that. Okay, Willem, that was, as always, absolute privilege to talk to you. Thank you very much for your time. That was absolutely fascinating. And I'll see you tomorrow.
Okay.